Objectives here. The first objective of the three is to talk about motion in terms of a frame of reference. And that's a big important part because most people don't think about frames of reference. And I'll explain in a minute the difference between the Earth being a frame of reference, being the object you're on, being the galaxy that you're in, and then calculating displacement of an object, and then finally constructing position versus time graphs. Something that's a little bit interesting. So let's first our frame of reference. Now, our frame of reference is a way of specifying where you are in space and time. So with regards to what? For example, I'm pacing back and forth right now in front of the room. I'm probably pacing back and forth, I don't know, at a velocity of like 0.5 meters per second. Every time I take a step, it's about 0.5 meters, so 0.5 meters every second. So I'm traveling at a pretty low velocity, right? Now, I'm traveling at a low velocity relative to you guys sitting there, relative to the floor. Ever go to the airport before and you're walking and you're like, oh man, I gotta rush. So what do? You don't walk on the ground, what do you walk on? Yeah, moving runways, you're moving platform, that thing. It's pretty awesome. And you're like, oh, this is great. I'm barely walking, and you see people next to you and they're like running to keep up. Why does that happen? I mean, logically, why does that happen? Yeah. While you're moving forward, so is the ground below you. Exactly right. So in that problem, you change your frame of reference. So what happens is this. If there's somebody that's sitting, let's say that you're in a Stony airport, somebody's sitting waiting for their plane, and they see you walking on the ground, they see somebody walking on the ground, they might be walking at like 2 miles an hour, okay, about that rate. But they see you, and it looks like you're going much faster, right? And you might be going like 5 miles an hour, because the runway is going at 3 miles an hour, and you're going at 2 miles an hour, so together you're going at 5 miles an hour. But what about the instance if you are on a train, same idea, okay? And the train is moving forward, so the train is traveling, and you realize, you know what, I gotta get together into this train car because or the front of the train's got a platform, or somebody threw up and it just stinks down here, so they go, whatever, you deal with on the train every day. So you start walking forward on the train. To people that are outside the train, they're gonna see the train flying by, right? Barely. Imagine they can actually pick up on it. And they're gonna see you moving. So it's going to look like you're moving really, really fast. Again, the speed of the train plus your speed, assuming you're moving forward on the train. But if Sierra's sitting on the train, minding her own business, sitting there, and she sees someone walk by, it looks like they're walking at a normal pace because she's on the moving train with you. So she's on the train with you, so she's already moving at 30 miles an hour. You're only moving at 3 miles an hour, so it looks like you're moving at 3 miles an hour to her. Because her frame of reference is from the train. That's for her perspective. But for somebody outside the train, they see the train moving and you moving. So relative to that person that's stationary out there, you're moving at like 33 miles an hour. But again, to Sierra, you're only moving at 3 miles an hour because she's on the train with you already moving at 30 miles an hour. So frame of reference is extremely important when we talk about terminology here because you might say that the velocity of a particle or an object is 5 meters per second. Well, if I don't say anything else, I assume that's relative to the Earth. So if you hear that something is moving at 5 meters per second, you assume that's relative to a stationary bystander on the Earth. If you say, the person is moving at a speed of 5 meters per second relative to the moving walkway, well, if the walkway is 8 meters per second and the person is 5, now it's 13 meters per second. So it depends on the frame of reference you're looking from to understand about an object. Yeah.
So if you're not given a specific frame of reference, just assume it's the Earth.
Exactly. And we're always going to assume it's the Earth, but if you hear in a problem that, you're on a moving platform or you're on some sort of object that is coming from a different frame of reference. For example, 2 cars that pass each other. Ever pass on a car and you look out the window, what does it look like? When you pass, imagine going like 60 miles an hour. What does it actually look like?
It looks like when you pass someone like
closing traffic on a highway. Your parents are driving, you're just looking out the window, and you see the other cars going the other way.
It looks like they're still in real life, speeding past them.
Opposite direction, not same direction. If there's a car next to you and you're going next to each other, yes, it looks like they're still.
But it looks like they're much faster than you.
Yeah, if you're going opposite directions.
Like 120 miles an hour.
Exactly. If you're both going 60 and you pass each other, it looks like that car just went by you at 120 miles an hour. There's the other scenario where you're on the train. Right? and you're on the, maybe we take the 4, 5, 6 line. Okay, so you're on the 4, 5, and at a certain point in time, the 4, 5, and the 6 are kind of next to each other. For a little while, they're different elevations. You know, the 4, 5 is a little bit lower in the ground. But at a certain point in time, they kind of, you can actually see the train next to you. So if your train is moving at the same speed as the train next to you, it kind of looks like they're not really moving. Because you know, if you're both moving at 30 miles an hour, you look outside and you see the train next to you, you're both moving like this. So it doesn't necessarily, you don't necessarily know that you are moving at a certain velocity in that case. I'm trying to think. One more example. Where have you seen or another example that's similar to that? Can anyone think of something? I'm trying to think of something besides trains and walkways. An airplane, okay. An airplane. So if you're in an airplane and you're moving forward, it's the same idea as if you're getting the 500 miles an hour plus your velocity forward. If you happen to be able to have two airplanes next to each other, you probably wouldn't. If you did, that would be interesting to see because it would look like you're moving. Oh, there's a classical, not problem, but statement in physics where imagine if you were on a train, okay, and everything was blacked out. All the windows were blacked out, so you couldn't see outside the train. And imagine if the train was moving with a constant velocity. We're going to talk about constant velocity this year, what that implies. If it were moving at a constant velocity, you might not actually feel like you're moving. You might not actually feel like you're moving. When you're in your car, when do you feel that like jolting forward or jolting back kind of sensation? When does that happen when you're in a car? It doesn't always happen, that's why. Theo?
When you switch speeds or stop.
I like the first part and the second part, they're both correct. When you alter your speed or velocity, right? Or when you stop. So when you apply the brakes or apply the gas, accelerator or brakes, because both of those things are either acceleration forward or deceleration when you hit brake. And what you recognize in this class is that only when you accelerate do you feel that sensation of a net force in your body. And that's Newton's laws, I think it was MA. So when you're at a constant velocity in a train and the windows are blacked out, you wouldn't really know if you're moving or not. You can hear it obviously, imagine you have like noise canceling headphones and the train was running nice and smooth. You physically wouldn't know. If you're on those maglev trains, any maglev trains that have zero to almost zero resistance, you'll recognize that if the train were blacked out, you would not know if you were moving because they move at such a constant speed the entire time and they cruise nice and smooth. You have no idea what concept of it. The last part about frame of reference is to always consider, even though right now like you're technically standing still, imagine there were some alien life form, thousands of miles, light years away. But they had some technology where they could see our planet with a telescope that they've created, that they can literally see down to the surface. Okay, and they can see you. To them, it would look like you're moving. Why would it look like you're moving? Even if you're standing still. Why would it look like you're moving? Okay? Yeah, because the Earth is rotating. So the Earth is rotating on its 23.5-degree axis tilted. It's also revolving around the Sun, which is in the galaxy, the Milky Way galaxy, which itself is expanding. So in reality, you're kind of always moving with respect to the universe. But when we talk about this class, we say with respect to the Earth. Yeah.
What if they're also?
Well, then it's relative to their speed. So if they're moving at the same velocity, the Earth is rotating, and they're moving in a geosynchronous orbit, then it wouldn't look like moving at all. That's how satellites work. So a lot of satellites, when they're up in space, they go to the exact elevation that would create what's called the geosynchronous orbit, and the satellite hovers or moves with the Earth, and it stays above. So it depends on which way they're moving. But if they were moving against the velocity of the Earth, it would look like you were moving even faster. All right, so frame of reference. We assume Earth when not given anything else. Next, let's talk about displacement. Let's talk about displacement. So Anthony said a little while ago that displacement was the concept, he's heard of displacement as the concept of air displacing water, or object displacing water. And that's absolutely right. For volume and chemistry, that's what we learned. For physics, we're going to talk about displacement in a similar manner. Okay, but instead of a certain amount of volume being moved aside, now we're going to be talking about a dimension of length. So you're looking at like a three-dimensional displacement. This is one-dimensional displacement. And we'll talk about two-dimensional displacement as well. So one-dimensional displacement, this little gecko guy here on the page, started at some position, maybe, let's say, 24 centimeters, approximately, and ended around 84 centimeters. So what's his displacement or her displacement? 24 to 84? What is it? Okay, you'll be able to do this. Come on. Think about it. 8 minus 2 gives you 6, and you're at 84 and 24. So that's from the middle of the gecko's body, God bless you, to the middle of the gecko's body in the second scenario. But what if I had started measuring from the tail instead? What if I had started measuring from the tail over here? Now it looks like he starts at 7, but it looks like it ends at 84. Can I do that? Can I use my measurements of the back of the gecko and then suddenly the middle of the gecko at the end? What should I have done?
Couldn't you do that because it would still be the same distance that he's traveled if he's like the same size both times?
Well, what should I do over here, Anthony? That's my question. Because if I calculate from this 7 to 84, it's not the same as the 60, so what should I do?
You would calculate to the end of the tail on the other one also.
Yeah, so if you're going to measure an object's displacement from the end of it, meaning the back of it, you need to go from the back of it to the back of it. So from 7 to 67 is still a displacement of 60 centimeters. So what I'm getting at is this. If you want to find displacement, you look for the final position minus the initial position. And you can put a delta here in front of the x if you'd like to. You could write delta x equals xf minus xi. That's fine. You could definitely put a little delta right in front. Now, I'm not putting a delta because on your formula sheet I don't. It just gets a bit cumbersome to run deltas everywhere when you're using x in a formula. So I'm not going to use delta here, but this x means displacement. Displacement is defined as the change in the position. What does delta mean?
Change.
Delta means change. So I'm not putting delta here because in the definition of displacement, the word change is already there. I know that I'm looking at xf, the final position, minus xi, the initial position, or the starting position. Okay? So that's what displacement is. Now, let's look at the same problem, but imagine this gecko started at 84 centimeters and ended at 24 centimeters. Well, then I would have to subtract. So a minute ago I did this, right? I did this, and this is what we got. But imagine now we reverse, and the gecko starts over here and ends over here. What happens to my equation? It flips. So it becomes 24 is the final position. Right? Imagine this is now xf, and this is where the gecko starts. And we take that gecko and make him go that way. Well, it's 24 minus 84. So what can you say? What can you generalize as a statement about displacement? Displacement?
It changes depending on what the object or the direction.
Direction, there it is. It changes depending upon the direction. Okay, so displacement, we can say, we should use this term to define the next chapter. Displacement is a vector. Displacement is a vector. It is important to understand the magnitude of the displacement, in this case 60 centimeters, and the direction it is moving. So if I go from right to left, I'm clearly moving in the negative direction that way. If I go from left to right, I'm moving in the positive direction that way. So the direction I move in is important to understand displacement. You have to take into account the negative sign when applicable. Klaus, read for me nice and loud, please. Sorry. Oh, go ahead.
The space shuttle takes off from Florida and circles the Earth several times, finally landing in California. While the shuttle is in flight, the photographer flies from Florida to California to take pictures of the astronauts when they step off the shuttle. Who was the larger displacement?
The astronauts or the photographer? Astronauts or the photographer? You need to draw yourself a diagram too. Think about it, right? So, draw yourself the Earth real quick and say to yourself, well, here's the Earth here. Let's say we got, that's California out there. There's Florida. Here's New York up here. Here's the rest of the U.S. So the person takes off from Florida, the astronauts. They loop around the Earth a few times and end up in California. The photographer leaves from Florida, hops on a flight, maybe doesn't take a direct route because the jet stream, ends up in California also. So the route that you see in black is the astronauts. The route that you see in red is the photographer. Theo, who undergoes a larger displacement? I saw your hand.
What way does the space shuttle go?
Doesn't matter.
Doesn't matter.
No?
Then the space shuttle.
In the space shuttle?
50.
33, 33, 33. What's the third option?
Oh, same.
3 options, yes. Because I mentioned that one. Why would it be the same displacement? You want to get?
Because they're going to the same place.
Yeah, think about it. What's displacement? Think about the definition on that slide. What is it? The change in objects. Swipe up, come on.
In position.
Position. The change in the object's position. What was the initial position for both of these, the photographer and the astronaut? What state was it? And what was the final position for both? So, we have to now write this down. So first of all, it's the same, but we have to make this conclusion. And this is a pretty amazing conclusion. Displacement does not take into account the path traveled. All that matters is the initial and final position. So if I walk around the room and end up right here, what's my initial position? Right here. What's my final position? Right here. So have I moved technically according to displacement? No, I haven't. So we're going to talk about how displacement and distance are different now. So if I literally walk around the room, come right back here, my displacement is 0. 0. Because my initial position, my final position are identical. So if I were to subtract those coordinates, I gotta do this, ready? About 5 units, and about 5 units. I'm back to here. What's my displacement? It's 0. There's no displacement here. Yeah. The path traveled. Okay? It's conservative. We'll talk about conservative things that conserve energy. Path travel makes no difference. Okay? Now, can somebody tell me what the difference is, ready? Between displacement and distance. Displacement and distance. Katie. Distance is the path traveled. So if I do this, ready? I walk to here. My displacement is positive 5 meters. My distance traveled is positive 5 meters. Now, I go back. My distance traveled from over there to here is 5 meters. But my displacement is negative 5 meters. So the positive 5 I walked and the negative 5 from displacement cancel out. So that's why I go displacement. But for distance, I walked 5 meters and another 5 meters. So I walked 10 meters in distance. Again, distance is the path traveled. Displacement is the change in position. Okay, distance is the path traveled. We're going to see that now. Okay, maybe in, let's see. How soon? In a little bit. Okay. Take a quick look at this table, and this is kind of what we were talking about. So clearly you can see that displacement is a vector quantity because of the fact that we can see that if it moves to the right, as seen on the left-hand side diagram, all of these displacements are positive. Okay, all of these displacements are positive because you're taking a larger number and subtracting a smaller number. When in doubt, think of a number line. Think of a number line. If you want to think about a number line, you have a positive value here, and you have a negative value here, and you have a final minus initial. If you do a positive minus a negative, what's minus a negative mean in math? You have to do. You have to actually add them. Like 5 minus negative 2 is really 7, right? So if you start over here at negative 2 and go all the way to 5, that's a displacement of 7 meters. But if I start at 5 and go back to negative 2, that's a displacement of negative 7 meters. So on the right-hand side, you're seeing all the examples of negative displacement. All right, questions on displacement so far? Does it make sense, the idea? The change in an object's position is what we're looking at. The position of the object. Okay, let's take a quick look at one of our first formulas we're going to use this year. Now, I think actually, can somebody do me a quick favor? Check Moodle real quick under documents and handouts. Tell me if the formula sheet's up there. I think I'll put it up.
It is.
It is. Okay, so all go, please everybody do this now. Go to Moodle. Go to Documents and Handouts on Moodle. And under Documents and Handouts, load the formula sheet. And please save it to Notability right now in your physics subject folder. It's important, that's why I'm wasting time, so I'm going to tell you to do this. And please take the minute it takes to do this. Again, open the formula sheet under Documents and Handouts. Save it to your Notability folder. Save it as formula sheet if you'd like to. Here's the reason I'm having you save it. Throughout the year, we're going to use, I don't even know how many. What do you think? It's probably like 40 formulas on there if you do it real quick, right? We're going to use every single one of those formulas. But for you to do well in this class, I highly recommend that you annotate your formula sheet throughout the year. So for example, V equals V bar, I'll explain what the bar is. V bar equals X over T. Isn't it the first formula on there? So when we're talking about this now, what should you probably do on that formula sheet? Yeah, talk about what it is. You could write average velocity, which is what V bar is displacement over time. So maybe write a little note in the margin, in maybe really small fonts on the left of it to the right of the formula, so that when you're at the midterm, the best way to study besides examples and labs and homework and all that stuff is literally go through your formula sheet. If you know what every formula is used for, if you know what instance you may have to utilize it, then you'll understand how to solve a problem based on the context. Yeah?
I know that this is maybe a premature question.
Cumulative, the final is cumulative.
For tests, are we to memorize?
No, okay, I have a formula sheet, what's the word, laminated, so I just give you formula sheets before every test.
Okay.
So nice.
Yeah. Now, remember I was talking about the subject test in physics? If you are taking that though, no formula sheets allowed. So, as much as I'm going to give you formulas all year, if you're going to take the subject test, I recommend that you start memorizing, make flashcards, make a ring of flashcards. Formula on one side, definition, and example on the other side. And when you get to this SAT subject test, you should be proud of that.
On subject tests, aren't you allowed to keep notes in your calculator?
Are you allowed to keep notes? I think the physics test has no calculator. They make the numbers very simple. I think they make the numbers like 10, 5. You can check, look into it. Yeah. You could definitely bring a graphing calculator. If you have a proctor that knows what they're doing, they'll go around and make it clear your memory. If you have a proctor that doesn't know what you're doing, they probably won't. But I'm not sure if you can actually use a calculator. I know on one of the math tests, the subject test, you cannot use a calculator. There's one of them. One of them you can. I'm not sure about physics, if you can use a calculator. So, back to this question. So, we're back to the statement. Velocity, average velocity in this case, you should maybe put a little note. Anytime you see a bar over something, it means average. Okay? That little bar over the top of the letter V means average. In physics, we're going to use the standard units of the metric system. So, our standard unit of length in the metric system is what? Meters. Meters. You're going to hear meters a lot. Our unit of time in any system is the second. Okay, the second. So this is a unit of meters per second. Whenever, you write this down also, whenever you see my notes and they have bold things like this, it means units, dimensions. The little bracket around the M over S is meters per second, like miles per hour. Okay, it's a velocity. Velocities are measured in distance, or I should say a length over time. Length per unit time. That length might be given as 3 inches per hour. And it's a little snail. And the snail literally moves 3 inches per hour. Or maybe it's given in miles per hour, it's a car. Or meters per second, as we're seeing right here. Let's take a look at an example. So during a race on level ground, Jamie drives her go-kart with an average velocity of 6.02 meters per second east. What is her go-kart's displacement in meters after 2 minutes and 17 seconds? Pretty straightforward problem. But I'm doing this, we're going to do this slowly because I want you to see the approach I always want you to take. Remember for the problem sets, I showed you a format that helps? So who remembers from the problem sets when I went over the format? What do you want to list first? First thing to do in these problems is to list, Ellie?
6.02 meters per second.
What is that though? What is it? I need to give it a variable. Is it time? Is it...
Oh, it's distance.
Look at the units. Meters per second. Distance would be measured in meters. Distance is measured in meters, so is displacement. Something that's measured in meters per second is like miles per hour. What does miles per hour describe? Your what? Yeah, so that's your velocity. And read right before it, Ellie. Look. See the word average velocity? That tells you that this is V bar. So you start with V bar equals 6.02 meters per second. I wish one of the TAs were here tonight. I can't emphasize this enough. Units tell you everything. The units tell you everything. So, when you're looking at velocities all year long, it's going to be meters per second. Maybe kilometers per second is converted, which means conversion, but it's the length over time. So, Ellie, when you saw meters per second, length over time represents velocity or speed, depending on the problem. Okay? Unless you see something else, you know that it is. If you saw just meters, that's what displacement or distance is. So yeah, that's what we have, and it's to the east. Which way is east, everybody? Please, I hope we know this. Which way is east? Right, thank you. To the right is a positive velocity. To the left would be negative velocity. How do I know that? Because a minute ago we said that velocity was displacement over time, right? If velocity is displacement over time, if I go left and my displacement is negative, then my velocity has to be negative because I'm going in that direction. Okay, so depending on the direction you're moving. So since it's moving east, it's a positive velocity. What else do I know? What's my other given? Remember, list the givens, list the givens, list the givens. Honor. Is the... Now, if that's true, can't I just jump right into the formula and say this? Right, that was the formula we wrote down a little while ago from the last slide. And our goal is to find displacement. So we're looking for x. So this was step 1, right? List the givens. Step 2 is list the formula you want to use. Step 3 is solve that formula for the given variable or for the desired variable. Can't I just go ahead and plug in my numbers and solve? I'm kind of prompting you to say, yeah, you can just now. Here's why. Klaus, why can't I just plug in these numbers like the way they are?
They try to transform the minutes into seconds.
There it is, good minute. Okay, you see here, nothing about minutes in these units. This is in meters per second. So I can't have minutes, they're not going to balance out. Units need to balance. So what's 2 minutes and 17 seconds, Katie? 137 seconds, very good. So what I do in my notes is this. Whenever I'm working on a problem, I convert right there. And I write this, just equals 137 seconds. Okay, now step 3 will be down here. Add a little room. But we have to convert our units. And I'm going to prove to you why that is when we actually solve this problem right now. I'll show you in a moment how the unit cancellation works out. Step 3 was to solve the equation for the desired variable. So, hypothetically speaking, I'm going to point real quick. Take a look at where I'm pointing. We want to solve, in this case, for x right here. If this was a number and this was a number, how would I solve for the missing variable x, Natalie? Yeah, whatever this would be. If this were 5 and you're dividing by 5, you multiply by 5 here, multiply by 5 here. So since time is some parameter, some value, let's multiply by time on both sides. Okay, let's all do this. What happens to time on the right-hand side? Cancels out. Giving me the formula I'm going to use, which will be x equals, and I'll just leave it the way it is, but the order doesn't matter, t times v bar. So that is what we call our generic solution. Our generic solution. So we've got our givens, our original formula to use. We solve that for our generic formula. And what was step 4? Once we have the generic solution? What was step 4? Once we have the generic solution, what should we do? The actual or specific solution. Either word's fine. So how do I do that? How do I get the actual solution now? How do I get the actual solution now? Alejandro, what do you got? How would I get the actual solution? What would I do here?
What would you just plug it in?
Yeah, so tell me what I'm writing. Go ahead.
Well, it's 137 seconds and then 6.02 meters per second.
Perfect. Now, Alejandro, follow-up question for you. Why does it make sense now that we converted this to seconds based on looking at the math that's going on here? Why didn't we leave this in 2 minutes, 17 seconds and multiply by that?
Because it's meters per second.
So what's going to happen?
It's gonna cancel.
What's going to cancel?
Seconds.
Very good. Seconds here are in the numerator, aren't they? And seconds here in the denominator. It's like dimensional analysis all over again, right? Seconds cancel. If this had been 2 minutes, 17 seconds, or even if you converted 2 minutes, 17 seconds into, what is that? It's about 2.3 seconds. 2.3 minutes. If you converted 2 minutes, 17 seconds into a decimal, it'd be like 2.3 minutes, because 17 seconds is a little bit under a third of a minute. So this would be units of minutes. This would be units of seconds. You can't cancel minutes with seconds. So as Klaus told us in the beginning, we've got to have the same units. We've got to cancel these seconds here and here. So what's my answer? 824.74. Point what? 74. And my only leftover unit in this problem was right here. Meters. The only units left over were meters. Okay? So at this point I know that my answer is meters. How else do I know that my answer is in meters?
This is your displacement.
Because it's the displacement. Displacement is a measurement of length or change in position. Questions on this problem? Yes?
That's not exactly on this question, but it's like in general. In general, like how many, how would be like a surrounding decimals? Like how far
Yeah.
does it go?
So, because I'm not a stickler on stick figures and stuff, on the test I usually indicate for math problems the random nearest tenth.
Okay.
Unless I specify otherwise. But in the directions at the top, almost all problems I put nearest tenth. Okay? Unless it's a problem where maybe the answer is like 0.0032, it's like a coefficient of friction you're solving for, I might say, you know, give me the nearest 10,000. You know? Or I might say scientific notation, something like that.
And because this is science, obviously you want decimals.
Yeah, you want some decimals, but the thing is, like, we were talking about the whole idea of precision in the other class. You guys haven't gotten to the lab yet. We're going to do the lab for you guys on Monday with double. If you're measuring your height, would you ever say, I'm for example, I'm 5'7". I would never say, I'm 5'7.239 inches. Like, it doesn't make sense, and I can't measure that precision. So if I were measuring like the length of an iPad, you're not going to say it's 9.1027434 inches. How could you know that? You can't measure that precise. So use common sense as well as scientific approximations. So if you get an answer, and your final answer hypothetically is like the square root of some number, right? Say you have to do a lot of square roots here because you have things that are square. So imagine your answer is the square root of 166.34. Well, that answer is going to have an infinite amount of decimals because it's the square root of a non-perfect square. Please don't list 12 decimals. It doesn't. You can't do that. It's not really that precise. You can't make that. You can't make that assumption that you know it's the nearest 13 decimal spots. Sure, if you're a research scientist in a lab with extremely sensitive technology and equipment, you can measure things, maybe not displacement or length, but other things to 20 decimal spots and be accurate. Okay? So over the weekend, whatever. Okay. So the other day we finished off with the idea of determining how far the driver drove the go-kart based on the velocity and time they spent. So today what we're going to do to start first, and we alluded to this the other day when we were talking about distance and displacement, is quickly talk about velocity and speed. So for velocity and speed, if we want to think about the difference between the two, try and think about the difference between displacement and distance. So I went over this example, but I was like kind of walking in front of the room. If I walk from here to the other side of the room to the right, you'd say it's a positive displacement. And then we talked about how moving in the negative direction or the left, we'd say it was a negative displacement. We consider up to be positive displacement and down to be negative displacement. So that's all about the position you move. Now, distance though, and we're going to see how that relates to speed. Distance, anyone remember what distance was compared to displacement? Yeah?
It's like the total amount, like it's how far you walked, like not from your original position, but just how far, like total.
Yeah, how far, so like the path traveled, right? So if I walk around the room, we said how the displacement would be 0 if I didn't have the same spot I started. Because technically speaking, my final and my initial position are both at the same spot. But my distance traveled would be the length of the path that I took around the room. Now, the easy way to think about velocity versus speed is this. Imagine that you start somewhere, pick a city in the country. Nebraska. Is that a state?
A state.
Okay, that works too. So let's, So we start in Nebraska, and we travel from Nebraska to Arkansas. And for some reason, I happen to know that Nebraska, I don't know this, is 200 miles. It's probably more than that. So let's say we travel from Nebraska, the great state of Nebraska, to Arkansas. And, were you?
Yeah, it was. That's crazy. I don't know why, but it always comes so random.
Let's say that the straight line distance between the two places, the straight line distance is 200 miles. Okay? Between Nebraska and Arkansas. It probably isn't. It definitely isn't, but it's pretty lucky guess. Let's say the straight line distance is 200 miles. What do I mean when I say straight line distance?
Directly there.
Directly there, okay.
Well, not like by road.
Yeah, not by road, right? Not by some curvature. So directly there. So how would you ever travel directly there? What kind of a vehicle would you need? Plane. What else? A jet. A train sometimes, but a train still does curve a little. Trains have minimal curves. Maybe like a hovercraft, something like that. Because even a plane, we know, right? We talked about this in this class. Did I mention how planes don't really take direct routes? Right? Yeah, planes follow the jet stream. They follow a lot of different things in the air to avoid turbulence. So they don't take direct routes, actually. And they also compensate for the Earth, moving itself. So let's say the direct line length is 200 meters. If you travel on a road between Nebraska and Arkansas, what can you conclude for sure?
That's not the direct.
Not the direct, good.
It's going to take longer.
It's going to take longer. What do you mean by take longer? Time or?
Well, there's more miles.
Oh, yeah, there's more miles. So it's a longer distance when you take the road than you go a straight line displacement. Here.
You also can't go as fast.
Yeah, you also can't go as fast. There's limits to that, depending on the road that you're on, right? If you're on a road and you're on a highway, then you're on a local town. You have to merge onto a highway. You have to change major highways. So you're adjusting your speed along the trip, not necessarily velocity. So let's write down that the road would be greater than 200 miles. Okay, traveling on the road would be greater than 200. But you don't necessarily know what it is. I mean, if the road went directly from Nebraska to Arkansas, and obviously we wonder what part of Nebraska, because it is a state, and what part of Arkansas. But let's say there was a road that traveled directly to it, then maybe the road would be 200 miles, and so would the displacement. But there's a very, 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 very slim chance that would happen. So technically you could put greater than or equal to, because it could be equal to 200, but in reality, it's most likely going to be larger than 200 miles if the displacement is 200 miles. So then we go back to the idea of velocity and speed. Now, your average velocity on a trip, if you remember from the previous class, was what formula? What did we use when we said average velocity? Average velocity, Nat?
X over T.
Yeah, average velocity was displacement over time. So in this case, your average velocity would be the 200 miles of displacement, right, in blue on the right here, over however long it took. Let's say it took you 4 hours. Well, we're on a hovercraft now for the direct one. So this is for the direct one. Let's say it took only 3 hours. So you travel 200 miles in 3 hours. So we're looking at how much? How fast of a trip or how fast of a velocity would you average? 200 miles in 3 hours is definitely more than 60 miles an hour, right?
60.
What is it going to be exactly?
60.
Not exactly 60.
It's like 66.
Oh, 66?
I don't know, I'm just doing yes.
66.666.
Why did you guess that it was 66? Was it a complete guess?
Because 300 divided by 3 is 300, and I just found that. It seems pretty complicated.
Okay.
I say because I know that 200 over 3, if you get rid of the zeros, it's just 2 over 3, which is 2/3. So it's going to be 0.666 repeating.
That's what I thought you were seeing also. So look at the 2/3. For a minute, forget the zeros, right? Wouldn't that just be 2/3? which is 0.6 repeating, so you were on the right track with 66. So anyway, 66.6 repeating miles per hour. You can definitely use a calculator in the class. It's not a problem. Okay, so 66 2/3 mile per hour. That would be your average velocity on this trip if you were going a straight line distance, but you're not. You're not. So now I'm going to tell you that instead of being greater than 200, let's say that the actual distance you traveled, okay, the actual distance traveled is 270 miles. Okay, there's another 70 miles of surplus because of all the curving and the winding and the towns you have to go through and the mountains you have to travel through and the tunnels you're going under and whatever not. So it's a longer distance, so it's 270 miles. What would my average speed be if it was 270 miles distance now over a time period of still, again, 3 hours? How would that change? Theo? Question? Well, what would you do to calculate your average speed? Try and think of the fact that velocity is analogous to displacement, speed is analogous to distance. So how would that formula change, right? A minute ago we used velocity equals displacement over time. What is speed going to be equal to? Help me out, Sarah?
Velocity over time.
Not velocity over time, because if we took velocity over time,
Speed over time.
it would be a different unit than the acceleration. Actually.
T over M.
Distance over time?
Why distance over time?
Because you're replacing displacement with distance. They're both the measures of length.
Of length. Think about speed. Isn't speed still miles per hour?
Yes.
Like if you said how fast are you going in a car, you give the speed. It's the speedometer usually. You don't usually talk about velocity, talk about speed. Speed is still length over time. But speed takes into account the distance traveled. So in this case, we're going to say distance over time. As opposed to, again, earlier, where we saw it was displacement over time. So our distance traveled this time is going to be 270, no longer 200. So let's go ahead and use 270 now. Over, what do we have as a time period still? 3 hours. So in this case, what would our speed be here? Yeah, you'd have to travel really fast for this to work. Would you be able to complete this trip in 3 hours, you think? Probably not. Okay? So to keep up, your speed would have to be greatly high, much higher than your velocity was in order for this to work. So a lot of the time, when you consider the distance traveled, and you take a straight line distance, and you don't take a straight line distance, the time period usually ends up going up. Usually it takes you a lot longer to travel that curved path than the straight line distance, which makes sense. Think about when you were a kid, right? If you were playing, I don't know, what was it called? Not tag. What was the game you played when you were younger when you had to... Not hide and seek, but like the more like, when you were a teenager you played. Manhunt, thank you. So in Manhunt, if you saw someone in Manhunt, you wouldn't take some roundabout route to get to where you needed to get to or capture the flag or whatever it is. Unless there was an opposing team you could get around. But if you saw the goal, like or the I don't know, end zone, but the final destination to get to, you would take the straight line distance because it would take you less time. So when you travel a certain distance here and it's on a curved path, it's going to end up taking you a longer time period. So what we're going to notice is that our speed and our velocity are two different things. Okay, and it depends on the problem, the context of the problem, to see which of them you're figuring it out. So on your test, I might say to you, I'll go do an example in a minute, but a person travels from point A to point B, calculate the velocity. Well, compare that to the speed if the distance traveled is this length instead. So you're comparing those two values. Or maybe you end up in the same spot you started. So the velocity would be 0 and the speed would be something else. But the difference between the two is very, very small, but there is a difference. Again, distance over time gives you speed, whereas displacement over time gives you velocity. Okay? So when you're in a car, again, you're measuring your speed. You're not measuring velocity. When you step on the gas and you see the speedometer change, you're seeing that little arrow move up because it's your instantaneous speed. It's the speed the car is currently traveling at that it's measuring. It's not really measuring the velocity of the car. Okay? All right, let's look at
Velocity, is it like when you have something where it tells you like 200 miles of speed? Like, what's the difference?
So it would depend on the problem. So in the context of a problem, if you're given some sort of geometrical arrangement and you're told that, a person starts at point A, travels east for a few miles, ends up at point B, then travels south for a few miles, ending up at point C, right? And you wanted to figure out, and you're told that it takes this and this is, let's say this is 8 meters and this is 6 meters. And you're told that it takes this person 10 seconds to do it. Well, if you want to try to figure out the speed, you have to find the distance traveled, which is how much? 14 meters divided by the time it took, right? But if somebody said calculate the person's average velocity during that trip, the average velocity is the displacement, which is this, over the time. So for velocity, you would end up using, to find average velocity here, you'd end up using 10 over whatever the time period was. But to find the speed of the person, you would use 14 over whatever the time period was.
So speed is like the whole thing, and velocity is just from the start to finish.
Okay, because again, velocity is taking into account the displacement, which is start to finish, whereas speed takes into account the distance, which is the path traveled. How did I know this is a 10, by the way? Anybody? Good. Pythagorean theorem. Or you know your triples, right? 3, 4, 5, 5, 12, 13, 8, 15, 17. You should know a few of those triples. You could always calculate it using the Pythagorean theorem. All right. Before we get into that example I wanted to do, let's take a look at this graphically. Let's take a look at what's happening here. So, we talked about speed versus velocity. Now let's focus specifically on velocity. Okay, let's focus on velocity. And what I want you to recognize is that if you recall from your math class, slope is really a rate of change. What does it mean on a graph if the line looks like this? The slope is what? Okay, well, I wouldn't say increasing. The function is increasing. The slope itself, though, is what? What's the word you want to use? Positive. You don't know if the slope is increasing depending on curvature. So the slope can be positive for a graph like this. For a graph like this, everybody? What about this?
Neutral?
Let's say 0. And let's use the number 0, 0 slope. Instead of no slope. And I'll explain the difference there.
Isn't this no
And
slope?
well, this we're going to say undefined. We're going to stop using the term no slope because some students think no slope means undefined. Some students think no slope means no is in. Like if I had no money, I have $0, right? So some students confuse no slope with either 0 or undefined. So let's forget no slope. Let's use the terms 0 slope or undefined. Now, we're going to talk about that specifically here because we're going to recognize that our average velocity formula was displacement over time. Well, that's just a slope, really. And think about it logically. Slope was rise over run. Change in y over change in x. That's what this is here. It's a change over a change. It's your displacement over your time period. How much your position changed, final minus initial, over the time period. T initial is usually 0, so it's usually just the time period in general. But what we're going to recognize is that velocity is really a rate of change. Velocity is a rate of change. So velocity is kind of like a slope. So let's go ahead and draw some graphs now. And I'm going to explain this a little more in detail with graphs. So draw yourself a first quadrant, please. Do we understand what I mean when I say a first quadrant? Okay, we don't need the other 3 quadrants right now. Let's label the x-axis time, measured in seconds. And I'm going to use the word, actually, I should correct myself. Let's label the horizontal axis time. Why did I not say the x-axis anymore? Because it's now no longer called the x-axis. It's called the time axis, or the horizontal axis. The vertical axis, we're going to label displacement. But that's an x, even though we're used to that being a y-axis. So the vertical axis is displacement, or position. The horizontal axis is time. It is time. And a lot of the time we call these position versus time graphs. So let's think for a second. I'm going to draw a graph real quick first. Let's give ourselves maybe 4 increments of time. each being 1 second in length. Let's label the vertical axis with units of meters going by 2. 2 meters, 4 meters, 6 meters, and 8 meters. And let's go ahead and label some points on this graph. Let's say we're starting here, and we go here, here, and here. Okay, and we'll say there's our linear function representing the action of what's going on. So, what does this tell me? How could you describe this graph? Think about functions. Think about the horizontal axis as your independent variable. You could say, at time equals 0, this person is a position of what? How far from the origin? 2 meters away. After 1 second, though, they're now how far from the origin? After 1 second, right, that's the x, how far from the origin are they? Meaning, what is the horizontal value here? Leo?
2 meters.
2 meters from where?
Where they started.
From where they started, okay. But they started 2 meters from the origin, so how far from the origin would they be then?
4 meters.
4 meters. So, everybody visualize for a sec. It's easier if I demonstrate probably. Think about the podium as the origin, okay? If I'm trying to describe this graph here, I would start here. So this is where I'm starting. So time is not elapsed. You're sitting there with a stopwatch, right? And I'm starting, well, 2 meters would actually be right this far. So there's the origin, which is the podium. You have a stopwatch, and you say, all right, now, ready, set, go, and you're timing it. And you hit the stopwatch and say start. Well, after 1 second has elapsed, I need to be 4 meters from the origin. So I need to take 2 steps in that first second. And now I'm 4 meters from the origin, or the podium, the origin, after 1 second has occurred. I started at this distance, or this displacement of 2 meters from the origin. Now I'm currently 4 meters from the origin. After another second elapsed, how far am I? I'm 6 meters. So again, I go to, after another second has elapsed, it means at 2 seconds, I go up, I see my dot here, my coordinate, I'm now at 6 meters. So again, I started at 2 meters, after 1 second occurred, I'm at 4, after another second, I took 2 more steps. Now I'm 6 meters away. And what you'll notice is that I'm moving away from the origin. So my slope is what? My slope is what? And give me general terms. What is it, Klaus?
Positive.
Positive. I'm moving away from the origin. My position is getting further and further and further away from the origin. What if I stopped at 8 meters at the top there? And make believe this is 8 meters. All right, I'm 8 meters away. What if I stopped and turned around and started going back toward the origin? Until I got all the way back here, and now I'm back at 0 meters. What would that look like on the graph? It would do something. It would do something. If I stopped for that time period, maybe I'd stop for a little bit. I'm not moving. I'm still at 8 meters. I'm stuck there. What, Ellie?
You go down
Why?
because you're like backing up.
Because you're backing up. Very good. So you start going back toward the podium until you reach it, and that's when you hit the horizontal axis further in time. So eventually you're going to intersect with that horizontal axis. So here, we could label this as like moving away from the origin. This is no motion at all, so you're standing still. And this is toward. Okay, toward the origin or toward the starting point. And you'll recognize that your slope changes depending upon your action. When you're moving away from the origin, you're moving with a positive displacement here. These are all positive displacement steps. So my velocity is positive. So my slope is positive. When I stop, what's my velocity when I'm standing still? What's my velocity when I'm standing still? 0? Okay, everybody should be able to answer that one pretty quickly. I know you're saying you're right, that's fine. When I'm standing still, my velocity is definitely 0. What's the slope of the line at the top? That little part that's flat. What's that slope again? Everybody.
0.
It's 0. Now, when I'm moving this way, my displacement is negative, isn't it?
Yeah.
So if my displacement is negative, it means my velocity is negative when I move this way. Isn't the slope also negative on that graph? So what could you say about slope? The slope of a position versus time graph indicates your what? Your velocity. Let's jot that down, please. Okay, the slope of position versus time graph is velocity. Okay, the slope of x versus t, that's position versus time. Slope of position is x versus time is velocity. Now look at your units, please. Tell me if that makes sense. Calculate the slope of the graph that is in the beginning. See the first part, the black line there in the beginning? The increasing black line? Calculate that slope real quick. On your own, go ahead and do it. Remember, if you forget, slope is change in y over change in x. Remembering, though, that x and y are just names. Here, it's really the change in the vertical component over the change in the horizontal component. Some of you might be able to just look at the graph and see the slope right off the bat, like, looking at your boxes and counting, or by inference. Others, you might want to calculate it. So remember that slope equals the change in the vertical component over the change in the horizontal component. I'm not writing change in y over change in x. Did you notice that? Because I don't want you to confuse the fact that the vertical axis is labeled as x. You're used to that being labeled y. So I'm writing change in vertical over change in horizontal. So I picked 2 points on the graph. Right here, this is the coordinate 3, 8. Back here, this is the coordinate 0, 2. So I've got 0, I'll point to it on here to make it easier. I've got 0, 2 right there, and I've got 3, 8. So I do my change in the vertical component, so it's 8 minus 2 over this 3 minus 0. The change in the horizontal. So I end up getting 6 over 3, or simply 2. And what are my units here? What are my units here? What are my units going to be? And you can take a look at your other axes to see if you're going to fill those in with. We got it.
2 meters over 1 second.
Yeah, so 2 meters per second. 2 meters per second. And units of meters per second are units of velocity or speed, either one or in, but they're units of a rate of change. So whenever you have a position graph on the y-axis, or a position on the y-axis and time on the x, you have a position versus time graph, you can calculate the velocity of the object at any point. Okay, in that red region, at the top, the velocity was 0. We don't know the velocity on this last part because I don't have any coordinates listed, but we do know that the velocity will definitely be negative in that last portion. Okay, so if you needed to describe this graph, you would say, in words, the object starts 2 meters away from the origin. The object moves at a constant velocity of 2 meters per second. For how long? For 3 seconds. The object stands still for, let's say, 2 seconds. Then the object returns toward the origin for another, whatever this is, I can label it, let's say 5 seconds, and ends up back at the origin, beyond where it started. Remember, it started 2 meters away from the origin, but it went all the way back to the x-axis, so it ended up at the origin. What if this object went beyond the origin? This is 0 here on the number line. Remember, this is like a number line. 0, positives, negatives. So if the person or the object continued beyond the origin, what would happen on the graph? What would that look like? It would be what? Yeah, it would go down or be negative. So you would end up in this 4th quadrant. It would continue, okay, down there. The velocity is still negative. If you're moving that way, your velocity is always negative. Once you pass the 0 point, we're calling this the origin, like on a number line, the origin. Once you pass that, you're in the negative area, or the negative domain. Therefore, in this case, I shouldn't say domain because you're used to that from that, the negative locations, that's where you go beyond this axis. You cross the horizontal axis. Now, the thing you cannot do really, though, is you really can't go across the vertical axis for these graphs. why do I not really consider what's going on over here? Why can't I, see how we went continue and past the horizontal axis? I can't go like this and continue past the vertical. Why can't I really concern myself with what's happening over here? Use common sense, not always just physics here. What's happening over here? Katie? Negative what? Has a negative what? You could have a negative. I could have started over here at a negative spot, but that would be a negative something else. There's a little thing, a little bit different here.
I have a question.
Okay?
So like, when, okay, so it has variables. Say like, you move that way, but that, like, this is your starting point, you move that way. Does that mean this is a negative?
Correct. That's exactly right. So a graph, like if you started at the origin and just moved that way, your graph would actually be like this. You would start at the origin, and if you're moving away from the origin in the negative direction, that means, remember, this is your direction, this is your position. If you're moving in the negative position, you start to go down. But you always go to the right. My question is, why can't you do anything over here?
But if you came back, so it would be positive.
If you came back to here, it would look like this.
So I'm just like.
So this graph, right, if I were demonstrating this graph, I would start at the origin, I would move this way for a certain period of time, I would about face, and I would turn back, and I'd come right back to here. And that would be that graph right there. Because that's negative velocity, that's positive velocity, negative slope, positive slope, which is your velocity. Okay, let's go back to the question though.
Because that's like the time, so you go negative time.
Can you have negative time? No. So you're never going to end up in these quadrants, right? In quadrants 2 and 3, or in this graph, quadrants 2 and 3 here, because this would be negative time, right? The negative horizontal. Look at the horizontal axis. The horizontal axis is time. Time always starts at 0 and it goes up. Or maybe it starts at 2, but it goes up. You don't start time at a negative number. Okay, it'd be like going backwards in time. So you're never going to see a position graph drawn on this side of the vertical axis. Okay? We're going to do more of this, trust me. We're going to do a lab that helps with these position time graphs. So if it's not exactly what you think right now, give it a little time, maybe tonight, practice the homework and try and see a little more. But we're going to definitely do a lab with this. And we're going to see these graphs come up again in section 2.2. Okay? Ben, what do you read for us? Nice lab, please.
A book is moved on a table around the edges with table dimensions of 1.75 meters by 2.25 meters. If the book ends up as its initial position, what is its displacement? If it completes its motion in 23 seconds, what is its average velocity? What is its average speed?
So, can somebody answer the first question for me instantly? The first question, you should all raise your hand actually. First question, read the first questions asked. The book ends up at its initial position. What is the displacement of 100 on 0? 0. We've said that many times. Imagine I'm the book. I take the book, right? And the book travels along this desk, like that. And then it comes back to here. It hasn't really moved in terms of displacement. But in terms of distance, it is definitely moved, right? How far has it moved in terms of distance? How far has it moved in terms of distance? 1.75 plus 2.25 plus 1.75 plus 2.25, right? If you're confused on what I'm saying right now, I'm just literally drawing a rectangle and completing the distance around it. What do we have? How far? How far? Come on, I'm seeing the same two hands. You guys, I'm asking you to add 4 numbers together. I want to see people that haven't raised their hand yet. How far has this person traveled with this book if it goes around the perimeter of that rectangle? These are easy numbers to add. $1.75 and $2.25 makes $4, right?
8.
So it's just simply 8. Just simply 8, right? Add these two is 4, add these two is 4. So the distance traveled is 8 meters. Remember, guys, you do get a classwork grade. I want you to be focused up here. Okay, if you're doing something else on your iPad, you're losing out. It's your own loss. Okay, I'm not going to come back there every 2 seconds to get people for stuff like that. Focus, please. The distance traveled is 8 meters. The displacement, though, is 0 meters. That part is good so far. Now, so we can simply say that obviously the displacement is 0. That's part 1. It says, what is the average velocity? What is the average velocity? Start with your formula. What's the formula for average velocity?
Average velocity was
X over t. Displacement over time. But what was the displacement? 0. So everybody, what's the velocity? 0. Okay, a bit, I don't want to say, I guess counterintuitive, right? You wouldn't think that your velocity, your average velocity was 0. If you ever take a round trip somewhere, technically speaking, your average velocity for that whole time period would be 0. Okay? If you get along on the railroad, go all the way out east, come all the way back to Penn Station, your average velocity for that trip was 0 miles per hour, whatever you want to call it. But your average speed was definitely not 0. So let's go ahead and figure out the speed now. So we were able to figure out the average velocity. What is the average speed? What's my formula for speed? How does that differ? We wrote that down a little while ago, Alejandro. What do you got?
Distance over time.
Yeah. So if that's true, right? Pablo, what's my distance travel? What's the difference here? How do I change this?
8 meters for distance over 23 seconds.
Yeah, so what do you recognize now? Suddenly you have a speed, right? Because you have traveled some distance. Although your displacement was 0, you have some speed. Okay, and 8 over 23 is going to be some fraction near 0.3. What do we get for an answer here? 0.35 meters per second. Why is that so slow? Well, it's so slow because use logic, right? Watch. This book traveled 1.75 meters, then 2 meters, then 1.75, then 2 in 23 seconds. I just did that in like, what, 5 seconds walking around? So that means it was literally moving like this speed probably, you know what I mean? Very, very slow. So you're getting a very slow rate. You need to be able to make sense of numbers. It's called number sense. Has anyone ever said to you, like, you know, if you're making like a cake or some sort of recipe, oh, this calls for 6 fluid ounces. Do you know what 6 fluid ounces looks like visually? Do you know what 3/4 a cup, looks like for flour? You should have a good number sense in physics. That's analogous to like baking. I'll give you an example. So 0.35 meters per second. Remember I gave you the example the other day? What's 1 meter per second? What was 1 meter per second? What does that look like? How far is a meter? About 3 feet or about a big step. That was the idea the other day I said, remember? So this is a meter per second. Every second I'm taking another meter step. So this is pretty much like a foot per second, right? 0.35 meters is around a foot. It's not obviously exact. A third of a meter because there's 3 feet in a yard and a meter are kind of close. You should know that this is about a foot every second. So if you were walking in New York City, you'd be walking this fast. That's what 0.35 meters per second is. So it's quite a slow speed. Okay, but you should be able to understand physically when things are fast versus slow relative to the world around you, the macro world, not on a microscopic level, because things are different there. Okay, but that's definitely slow when you're considering speed. Questions on this problem? Okay, so we have a displacement of 0, a distance of 8 meters, an average velocity of 0, but an average speed of 0.35 meters per second. All right. Next and final example. Can I get a reader, please? Nice and loud. Frankie, go for it.
2 students walk in the same direction along a straight path. A constant velocity, one at 1.50
meters per second.
meters per second, and the other at 2.1 meters per second. Assuming they start at the same point and at the same time, how much sooner does the fast student arrive at a destination of 500 meters away?
Well, right away you know that they're not going to arrive at the same time, right? It's like 2 people in a race. One's running faster and the faster one finishes sooner. So what approach might you take? Just use theory at this point. Forget giving this stuff. We'll list all that stuff in a minute. What's the approach to a problem like this? What might you do?
Well, you should find the times for both and then compare them.
Right? Is that simple enough? Does it make sense? It says how much sooner. So if I want to know how much sooner Alejandro beats me in a race, how much faster he gets there, well, clearly I can calculate the time it takes him. Maybe it takes him 10 seconds to finish the sprint. It takes me 12. So how much sooner? 2 seconds. So you need to find the time for person 1, the time for person 2, and subtract those times. Go ahead and practice. Go ahead. Try it on your own. List your givens if you'd like to. Okay, list your formulas. You can do this probably in like 30 seconds by just doing the numbers, but do me a favor and try and list this for now. Okay, just for now, list your givens, list your formula, go through the whole process. Feel free if you struggle or if you're confused to ask the person next to you, work with them. While you're doing it, I'll put up small things on the board so you can look to get yourself hints. I'll go through the whole process with givens and everything. We should probably open those windows a little air in. It's nice and... Yeah, those back too. I'll do it as well. Just because it's nice and cool outside.
That just reminds me of freshman orientation, where feathers all over the place. And you told us to open the windows to...
I do remember that. And that was in this room, wasn't it?
No, that was first.
Oh, 301. 302. I remember that.
Are you talking about feathers?
Yeah. Got an incident?
Still been full.
You weren't a freshman that year, was that yours?
Yeah, that was.
She does? Oh,
Yeah.
gosh. That was on that tree.
And we had the air conditioner on, and you were all upset because you thought it was circulating in the room more and just recycling the feathers.
I was allergic to
Yeah, I woke up with like feathers in the back of my head.
Right, eating feathers all
Oh, they
morning.
need to like.
And this paper got very upset.
I'm going to open this door to let a little cross freeze, but don't let them distract you. They're just doing a paper airplane lab. It's a new lab. Mr. J started this year. He does it in a scientific method for scientific reasoning. They try stuff out and see the hypothesis if it works. Take a little break real quick. Get up straight. So, we pick up here at this point. We've listed our givens, right? Now, we recognize that our general equation here is not solved for time. But we do need to figure out what time is in this problem. So we have to go ahead and solve for time. This is very, very, very important. You understand what we're about to do. It shows up in a lot of formulas. The easiest thing to do is to switch V and T. Literally. You can flip-flop these, and I'll show you why right now. But from this point on, you can always just switch these two if you need to get time by itself. Okay, but let me show you mathematically why that is. So you start by multiplying both sides by time. T cancels here, which gives you T times V bar equals X. Then you want to get time by itself. To get rid of V bar, you have to divide both sides by V bar. So you divide by V bar on both sides. The V bar cancels on the left side, giving you time is equal to X over V bar. So, again, from this point on, if you want to solve for time, just flip-flop diagonally. This works for all formulas all year long. If I had my density formula, this is a side note. Write a little side note over here, please. If I had density equals mass over volume, and I wanted to get volume by itself, I would literally do the same thing. See how time and velocity were to flip? You could switch volume and density. You could just flip-flop them. It always works. You learned about this, believe it or not, when you learned about proportions in your math class. When you learned proportions, either middle school or freshman year in Algebra 1, depending on where you studied and whatnot, you saw how proportions, it was called the products of the means equals the products of the extremes. You can always switch diagonally. Okay? Depending on the formula, you can switch. It does not matter though, they're all the same. So in our case, since we need to get time by itself, we have V bar equals X over T. You can say T equals X over V bar. You can just switch these two. But this is the reasoning as to why. Okay? Now, at this point in time, it's easy. You want to find the time for the first person it takes to complete the race, which is just X over V bar. The time it takes the second person, that's this answer right here, figure it out. The time it takes the second person to complete the race is X over V bar. For the first person, apparently it takes them, they're going faster. Oh, sorry, they're going slower. It takes them 333.3 repeating seconds. It takes the second person who's going faster 250 seconds. So how much earlier did the faster person arrive? What's the difference between these two numbers?
82 and 2/3 seconds faster.
83 and 2/3 seconds faster. Sorry, no. Yeah. No, 83 and a third, not 2/3. I think you, what did you do? 350 minus?
I did 33 minus 2. I realized you did wrong. I
Yeah.
did ask if it was 300 minus 250.
Okay, I was wondering where you got 2/3, so 1/3 still, okay? So this is how much sooner the faster person arrives than the slower person. So the slower person took 333 and a third seconds. The faster person took 250 seconds. So if you tack on 83 and a third seconds, that's how long it takes in the delay before the second person comes in to finish. Okay, simple formula, but just showing you how to use it. So, lesson 2.1, you should have gained the following information. Understand what displacement is. Understand velocity, displacement time, as opposed to speed, distance time. Understanding how to use the position time graph, and then obviously how to utilize the formula, velocity equals displacement over time. That was everything from section 2.1. I moved through this section at a slower pace than I planned to move through in others. Okay? And I did that for a reason, because I noticed people were struggling a little bit, and at the beginning of the year you got to get caught up to things. But as we go through the year, I'm not going to spend too much time rearranging simple formulas. I might just go right through the work. You have to keep up with it. So, if you find that you feel that if you find that you're a little bit behind or you don't understand something completely, please don't wait until you have 3-4 things that are confusing. Come see me as soon as possible to go over stuff that isn't 100% certain in your mind. Tonight you'll practice homework for this. Okay, that homework is due tomorrow. It's on the next slides this time. So one of the few times there's more than like 4 or 5 problems. Usually it's like between 4 and 6 problems. They're not that difficult of problems. Okay, there's 8 of them. So make sure you spend some time tonight on those problems. They're due tomorrow.